Okay, this next section is on collections in C Sharp, and I'll let you read most of the stuff for the details. I just kind of want to tell you in a nutshell what collections are and just an overview of the main collections, and then we'll look at the syntax, and I think we'll be done with this chapter, which means we still have to work with dates and strings. Anyway, so a collection, like there's all kinds of different data structures you can use in computer science, and you guys probably already encountered them. You might even know all what I'm about to talk about, but I just want to cover it in the interest of being thorough, and maybe talk about a little bit of the .NET and C Sharp specifics. But so again, just ways of collecting a bunch of data together and processing it using the characteristics of the data structure. So one you already know is arrays because we just finished it. So arrays are kind of like your first data structure usually. And just remember the characteristics: contiguous in memory, fixed size, all the elements are the same type. Those characteristics are going to be, some will be shared with collections and some won't. What I'm showing you now is the logical view of a list in principle, a linked list in this case, singly linked list. This is how they work. Whereas arrays are contiguous in memory, lists can be, they aren't necessarily. So they'll have a starting place that tells where the list starts in memory. They'll have a memory address where the first node is what it's usually called is. Then that node will have a value it's storing. In this case, we got integers, but it could be in principle anything. It could be objects of different types, like a dog object if you have a dog class, or it could be all the basic value types. In any case, whatever you store is like sometimes called the data or the payload is here, and then you have a link to the next node. Just like the start pointer tells you where to begin, this tells you where the next node is, and so on until you get to the end. This is saying null is the end. There's some kind of, usually it's null, a null memory address, but if the next link points to some signal marker that signals the end of the list, now you're at the end of the list. So what are the pros of lists? It's that your structure is always exactly the size of the data you're containing. So it's, if you have one piece of data, you have a list with one node. If you have 10 pieces of data, you have a list with 10 nodes on it. It's always exactly the size that it needs to be. No wasted space. Arrays could have wasted space because remember, they're fixed in size. So if you're working with sometimes 5, sometimes 8, sometimes 10, sometimes 15 in your data, do you make it 20? Maybe you never have 20. You know, the max you ever have is 18 or 19. Can you be sure? So that's one of the concerns with arrays. One of the drawbacks is you have to know ahead of time. With the linked list, you don't. You just add something to it, and on the fly, it will create the new space, the new node, and link it up. Now, here's what I'm going to say. The list in .NET, I think a particular generic one that's typed, is actually implemented with an array deep down. So it gives the appearance of being a list, but you just have arrays that are dynamically and allocated and deallocated, etc. So when you get to where how things are really implemented under the hood, sometimes it kind of, I think belies is the correct word, what's really going on. So at some point in one of your classes, if you have C Sharp especially, not C Sharp, C++ especially, you might implement this on your own in the classic way, which really is using links and not an array underneath. But that's neither here nor there. So you've got the list. The next thing you have are queues and stacks, which could be thought of as special purpose implementations. It's really more about the algorithm and how you add and remove things than it is about how it's implemented. So this is even farther divorced from array versus list. You can, what I'm trying to say is whether you use a classic real linked list that's not really implemented deep down as an array, where you actually create new nodes and link them up in memory, and they can be scattered all over memory that way, which is one of the drawbacks. They're not as fast because you have to look up where the next thing is each time you traverse it, right? That a queue and a stack can both be implemented using this, or they could be implemented using arrays. And that's not like a trick optimization. It's just like you're just using an array. Now the drawback is that it would be fixed in size queue, a fixed in size stack, versus dynamically, exactly the right size for the data stack or queue. But the thing that remains the same is how you interact with them. So for a queue, it's called, let me type it up in this address bar for you, FIFO, first in, first out. That's the principle. For stacks, it's LIFO, last in, first out. Oh, so the way that a queue works, here's a picture of a queue right here. You'll have something that's like the front of the queue, and you'll have the rear. So things that are need to be deallocated from the queue, they're the next thing to be processed. For instance, just think of like lining up at a theater. That's a queue, right? What's the processing? Buying your ticket. So whenever you buy a ticket, it pops off of the front of the queue and handles that. So 7 would get his ticket first, and then 2 would get his ticket. Now let's say 13 rambles up, like, what's the word I want? It's not rambles up. I guess that works. He comes, what's the word? Does walk awkwardly? Staggers up, and he's going to join the queue. He will be attached to the queue at the rear. So last in, last out. In other words, first in, first out. So this guy was here he lined up first, then this guy. So it's just, that's what a queue is. It's the fact that you have a front and a rear, a beginning and an end, however you want to call it, where the processing of the actual data is done from the front to the rear, and adding data is always done to the rear. So taking things off from the queue, always from the front. Adding things onto the queue, always to the rear. That's opposed to a stack, which is last in, first out. It's usually called push and pop. So when you add something to the stack, you add it to the top. So you'll have a new top. So if you pushed here, you would have a new rectangle, and this would move up and point to the top. Whenever you process something from the stack, it's called a pop. So you would pop off the top thing of the stack and process it again. Now your stack, and now your top's one down lower. So this is showing you side by side. This is actually nice. See, last in, first out. That's a stack, and then first in, first out. So showing you how he's lining up at the back. Side by side, you can see there's a bunch of other different pictures of this, right? Think of the stack is literally like the stack of plates at a buffet, where if you got somebody just washed the plate in the kitchen, I guess, and brings it out. Just one plate. I don't know why one plate, but one plate. Where does he put it? He pushes it to the top of the stack. So if somebody comes to get a new plate to eat their buffet, they take that one that was last put on. There are pros and cons. There are different kinds of algorithms that use this. There's a very, for instance, compiling a program often uses a stack cut underneath as this algorithm for making sure everything's balanced. Stacks are really good for balancing things. Queues are really good for fairness and processing. So the first thing that shows up is the first thing that gets processed. And if you abide by that strategy, instead of, say, if you did a stack, right, there might be some things at the bottom of the stack that never get processed. But if you do a straight up, no tweaks to it queue, everything will eventually get processed in the order that it came in. There is something called a priority queue, where you add a new thing to each. How you see how you've got A, B, C, D, E. Right here's the payload. If you attached another thing to it, it's like how important it is. Like the lower number goes first or the higher number goes first, regardless of the position in the queue. That could also possibly be unfair, because the things with low priority would never happen. And think about the example would be at the grocery store when you, I've got a million items, I'll let this person with one item in front of me. If that's your policy 100% of the time, if enough people with one item come up and get in front of you, you'll never get your shopping cart full of stuff processed. So we can talk more about, you don't even really need to know the purposes of them right now, just know how they act. The only other thing you have is called a sorted list. It's really what would be known as a dictionary, maybe in other languages, and there's other terms for it. But the way it works is you have a key and a value. The values are what you're actually interested in storing on the thing, And the key is where it's located and how you can reference it and get it back. So think of like, your address. Your address is for your house, or social security number. That's better. The key for you as a person in the tax system or whatever, the government, the federal government, is your social security number. That's the key. The value is the fact that you're a person, like your whole body, your whole identity is the is the value. It's a weird example, I know, but the key only serves the purpose as far as like retrieval and organizing, and the value, it could be anything. So you can like have a key that's integers and the values can all be strings, or the key could be integers. I mean, typically what you want it to be integers, probably. Sometimes it could be other things, but it could be strings too. But say the key's integers and the value is like a book, the whole text of a book, or it could be any object. You could have a bunch of dog class objects, right? I like to use that as an example for some reason, the dog class that we've created. You could store those dog objects keyed with a key, an integer key. So that's enough about that. The sorted list, the reason why it's good is because it's using a binary search algorithm. It's sorted, and then if you need to retrieve something, it's what's called big O of log n time. It's very quick, and which you should know from the binary search what I'm talking about. Every time you probe into it to find the thing, right, you reduce the amount of data you have to look through by half. So that's the advantage of a sorted list. What are the pros and cons of them? It depends on what your specific purpose is, and sometimes it's an art figuring out which one you should be using for your particular project. So that's a bit about collections. There's one other thing to say about them. I don't want to harp on this too much, but there's untyped and typed. Just kind of generally think you should be using the typed, the ones with the angle brackets in .NET. Back in the old days, you didn't have this, and what happened is whenever you stored something to a list or what have you in the past in .NET, what you actually would do is you would strip the information about the type of the thing that it was, whether it's an integer or a dog or I don't know, an array or whatever. If you're storing things on the list, it would strip all that, bear down to a generic object. It's just an object. What that meant was that you could store different types of data types together on one list, because as far as the list was concerned, they were all objects. And what that meant is that at programming time, at compile time, you would have to know what you were pulling off of a list, off of a queue or whatever. You would have to know, and you would have to cast it to that thing, or else you would get errors that your program would probably crash, because it has to know. If you strip everything that says that an integer is an integer and just turn it into an object, think of it as like an envelope in a letter. The letter is the part that, the arrangement of bits that tells you that it's an integer, right? That the integer looks like. And then the envelope is the thing that tells the program, your code and the processing, that it is an integer. So it says, okay, this is an integer inside this envelope. I know how to process it. I know what order the bits should be in. So if you imagine data types like that as envelopes, then if you strip those envelopes off, you just put the bits in. However, and you can mix things together, and you'd have to know when you take them off how to treat them. So that's where the casting is. Downcast, literally polymorphism and downcasting. It's kind of hard to explain this maybe, but that had drawbacks. It had convenience because you didn't have to worry about what you were adding to the list. You're like, I'll just add this to the list. But the drawback was that if in the other half, when you take something off the list and like, hey, I need to treat this. What do I treat this as? Is this an integer, or is this a string, or what? And that's where the problems would come in. So added to .NET is this thing called generics, and it's a way of creating the same. What it means is you can create the same objects or structures for something. The algorithm's the same, the structure's the same, but the data types are different. And when you're writing your program, you specify, hey, I want to use this list, but I want it to be a list of integers. And then it will check for you at runtime and compile time that you're working with the thing you said it was. So I have a list of integers. I have a stack of integers. I have a sorted dictionary of integers with strings, or string integer key, string value, or string key and string value, what have you. So all those things are checked, and they're less prone to errors. So make sure you read the book. It'll explain this to you maybe better, but in general, you want to use the latter kind, the typed kind that have the angle brackets. So in later videos, I'll show you how to. I'll probably do one example where I do the objects with the old-fashioned, and then the one. They're still both in the language, but then I'll do the typed ones, and so you can compare. It's probably been boring to look at this animated GIF for all this time, but so I apologize for that. But and when we come back, we'll do some specific examples. I've retooled my array thing, and I made the font bigger so we can read it easier. I'll see you in the next one.